Let's do some practice problems from Chapter 6. These are going to focus on the sections, topics covered in sections 6.1, 6.2, 6.3, 6.4, and 6.5. First, let's look at number 6.2 from your textbook. It says, calculate to 2 decimal places the formula masses of each of the following substances. Obtain the needed atomic masses from a periodic table. So we would look at A here and notice that there are 20 carbon atoms and 30 hydrogen atoms and 1 oxygen atom. And so I'd look up the molar mass or formula mass of carbon on the periodic table and see that it is 12.01. Notice I'm only carrying out to 2 decimal places. So I'm going to take 12.01, which is the mass of 1 carbon atom, and multiply by 20, because there's 20 of them. And then the mass of 1 hydrogen is 1.01, and there are 30 of them, so I'm going to multiply by 30. And the mass of 1 oxygen is 16, and there's only 1, so I just multiply by 1. And then you use your calculator, enter all of these numbers, and add them up. And I get 286.50. In calcium nitrate, I have 1 calcium. Calcium has a molar mass of 40.008. I should say formula mass. You can tell I use molar mass way more than I use formula mass. They're essentially the same thing, just different units. Then I have 2 nitrogens, and that 2 is coming from the fact I had 2 nitrates. And so there are 2 nitrogens, each of which is 14.01. So I'll multiply that by 2. And then there are 2 times 3 oxygens, which is 6 oxygens, each of which were 16.00. So I'll multiply that by 6. So my 40.08 plus 2 times the 14.01 plus 16 times 6 gives me 164.10. Technically, my units are AMU right now because I'm just talking about the atomic mass of this. All right, number 8 from Chapter 6. How many atoms are present in the following molar quantities of various elements? So I have 1.20 moles of gold. And the question is, how many atoms of that are present? So we know that there are 6.022 times 10 to the 23rd atoms of any substance in 1 mole. So I see here that I have moles, and I want to go to atoms. And because I'm going to atoms, that's the reason I'm going to use Avogadro's number. So 1.20 moles of gold. And we know that for every 1 mole of gold, there's 6.022 times 10 to the 23rd atoms. Gold. So this is going to be a pretty big number. 1.2 times 6.022 times 10 to the 23rd gives me 7.23. I only have 3 sig figs times 10 to the 23rd. And that's atoms of gold. Now, here's something interesting. I have the same number of moles of a different substance. I have 1.20 moles of silver. But the thing is, to go from moles to atoms is the same regardless of what substance I have. So for 1.20 moles of silver, I still have to cancel out the moles of silver on the bottom, and I still want to go to atoms. So 6.022 times 10 to the 23rd atoms is the only relationship I have for moles to go to that has atoms in it. And so therefore my answer is the same, 7.23 times 10 to the 23rd atoms of silver. All right, number 14. What is the mass in grams of each of the following quantities of matter? I have 0.85 moles of copper atoms. And this may be a little bit confusing because some students may read this and think, is that moles of copper or is it atoms of copper? Well, your textbook, for some reason, likes to be very specific. So it says moles, and then it says of what. So the unit that we're really interested in changing is right here, is the moles. So I have 0.85 moles of copper, essentially. And I want to figure out the grams of copper. And so I can look on the periodic table and find the molar mass, just like I could find the formula mass from the periodic table. And when I look there, I see that copper, 1 mole of copper, is 63.54 grams of copper. So there's my conversion. And since I have moles here in the top, I must have moles in the bottom of my fraction. So 1 mole of copper to 63.54 grams of copper. And then I do the math. 0.85 times 63.54 gives me, I only can have 2 sig figs because I had 2 sig figs here in my measurement, so 54 grams copper. All right, here we have D, 2.50 moles of nitrogen molecules. Again, it's told me nitrogen molecules, and it has also told me it's moles of those. And again, I want to focus in on the fact that we're being asked for moles. It happens to be of nitrogen molecules, but I don't want to get confused by the molecules. So I have 2.50 moles of N2. And the question is asking me for the mass in grams. So I have 2 nitrogens here. So 1 nitrogen, 1 mole of nitrogen equals 14.01 grams. So 2 moles of nitrogen, or N2, would equal twice that. So 2 times 14.01 grams, which gives me 28.02 grams for 1 mole of N2. So since I have moles of N2 here, then I put my 1 mole of N2 on the bottom of my fraction and the 28.02 grams of N2 on the top. And then using my calculator, I take 2.50 and I multiply by 28.02. And that gives me 70.05. But my 2.50 only has 3 sig figs. So this is going to give me 70.01. Excuse me. I just told you 3 sig figs. 70.1 grams N2. How many moles of particles are present in a sample of each of the following substances if each sample weighs 7.00 grams? I have a little bit of a typo there. So it's telling me I have 7.00 grams of N2O. Now, the textbook's just being really specific and telling you, hey, that N2O is present as molecules. That's great. It does not mean that I'm actually changing molecules here, because it tells me that my sample is 7 grams. And I want to go to moles of particles. Again, the of particles is just extra information. I really want to focus in on the fact that I need to go to moles. So I have 7.00 grams of N2O, and I need to go to moles of N2O. That's really what this question is asking. So to do that, I need the molar mass of N2O. And we know that N2O is 2 N's and 1 oxygen. And so I can go to the periodic table and find the molar mass of nitrogen, and it's 14.01. I'm going to multiply that by 2 because I have 2 of them. And the molar mass of oxygen is 16.00. And then I will add those 2 together to figure out my molar mass of N2O, which is 44.02 grams per 1 mole of N2O. Okay, so there's my molar mass conversion that I want to use to convert grams to moles. So 7.00 grams of N2O. Grams is here, and so grams needs to be in the bottom part of the fraction. So I put my 44.02 grams of N2O down there. And that, remember, from over here, was equal to 1 mole of N2O. So I take my 7, divide by 44.02, and I get 0.1590, but I only have 3 sig figs, so I'm going to go with 0.159, and this is moles. That's my answer. Okay. Now let's look at this next one, which is actually letter D. We have vanadium atoms, and there are 7.00 grams of vanadium atoms. So really it's 7.00 grams of vanadium. Let's just simplify that. And we want to go to moles. So I need to go to the periodic table and find vanadium, which is element 23, and I see that its molar mass is 50.942. Now, I'm only going to go to the hundredths decimal place, so I'm going to say this is 50.94 grams per 1 mole of vanadium. And then 7 divided by my molar mass at 50.94 gives me 0.1374, but I only have 3 sig figs, so it's 0.137 moles vanadium. Okay, next question. How many moles of each type of atom are present in each of the following molar quantities? How many moles of each type of atom are present in each of the following molar quantities? So I have 4.00 moles of NO2 molecules. And what I want to assess right now is, when I look at this formula, what do I have in it? Well, I have 1 N and I have 2 O's. And so that means I could say I have 1 atom of N and 2 atoms of O. Or I could also recognize that I have 1 mole of N and 2 moles of O for every 1 mole of NO2. So each of these relationships, this here and this to here, is a conversion. And I want to know the moles of each type of atom, so I'm going to take nitrogen first. And I have 4.00 moles NO2. And then I'm going to pick up my relationship, which said that I had 1 mole of N for every 1 mole of NO2. So therefore, I will have 4 moles. Whoops. Oh, my goodness. I'm going to have to erase. I totally did that backwards. What was I thinking? Okay, here we go. 4 moles of NO2, 1 mole of NO2 on the bottom, and where are we going to nitrogen? 1 mole of nitrogen on the top. There we go. So that gives me 4 moles of N in this sample. The oxygen, I have 4.00 moles NO2. And this time, I want to use my relationship with oxygen. And the relationship was 2 moles of O in every 1 mole of NO2. Right? That came from my formula when I broke it down right over here. So when I do this, we end up with 8 moles of O2. Excuse me, 8 moles of O. Okay, let's do the next one. I have H2O2, and that tells me I have 2 moles of H, just bringing that that subscript right on down, 2 moles of H in every 1 mole of H2O2. And also, there's that other 2 hanging out with the oxygen. That tells me I have 2 moles of O for every 1 mole of H2O2. So, if I start with 7.00 moles of H2O2, then I should have, for every 1 mole of H2O2, 2 moles of H, which gives me 14.0 moles of H. And since I started with 7.0 moles of H2O2, and I had 2 moles of O for every 1 mole of H2O2, this is coming from this relationship right here. See that? And then, again, 14.0 moles, only this time it's of O. Number 28. Based on the chemical formula H2CO3, write the conversion factor that would be needed to do each of the following conversions. So in letter B, we see we want to go from moles of H2CO3 to moles of H atoms. Again, don't get tricked by this. We're really more interested in the fact that it's telling us we're doing to moles of H. So we've got to go from moles of H2CO3 to moles of H. And to do that, anytime we're asked about an element that's within a compound's formula, we go back to the formula and we look at that element and we see what its subscript is. And I see that H has a subscript of 2. So that tells me that for every 1 mole of H2CO3, I have 2 moles of H. So that would allow me to convert from, say, 5 moles of H2CO3. I could convert using this equation, this relationship, to moles of H. All right, letter D says moles of H atoms to moles of O atoms. Well, when we look at H2CO3, we have the relationship that we just found for H, and we also have a relationship for carbon. Carbon. Just looking at carbon, thinking about oxygen. Looking at oxygen, thinking about carbon. Anyway, and you can see here that I've got 2 H's and I have 3 oxygens. So we put that together. 2 moles of H equals 3 moles of O. Pretty snazzy. All right, number 29. Determine the number of atoms in each of the following quantities of an element. So now it's asking me for atoms. And in letter A, I've been given 10 grams of boron. So I'm going to start with what I'm given, 10.0 grams of boron. And I have to think about how can I get to atoms? Well, I know that there are 6.022 times 10 to the 23rd atoms in 1 mole of any substance. Not any substance, any substance of which it's only present as atoms. And I also know that 1 mole of boron has a molar mass of 10.81. And I'm picking up this number from the periodic table. So I have 2 pieces of information. And I see that my grams start here. And that from grams, I can go to moles. And from moles, I can go to atoms. Okay, so let's do that. 10.0 grams of boron. And my plan was to use the molar mass first and cancel out my grams. So grams goes on the bottom, 10.81 grams of boron. 1 mole of boron is the rest of that conversion. Then next, since now I'm in moles, I can go from moles of boron to atoms of boron. And then I put that all into my calculator. And I get 5.57 times 10 to the 23rd. Atoms, boron. Okay, let's do neon. Again, I know I'm going to atoms, so I know that the 1 mole of neon equals 6.022 times 10 to the 23rd atoms of neon. And when I look at the periodic table, I see that 1 mole of neon equals 20.183 grams of neon. So I'm going to start with my grams, 2.0 grams of neon. And then I want to cancel grams. And I can see that right here, I have a mole to gram relationship. So 20.183 grams neon to 1 mole neon, which gets rid of my grams. Then I see, hey, I'm in moles, and I have moles over here, and it will take me to atoms. So my next step is to convert from moles to atoms. So 1 mole of neon is equal to 6.022 times 10 to the 23rd atoms of neon. And put it in your calculator. 2 divided by 20.183 times 6.022 times 10 to the 23rd gives me 5.97. Oh, hold on. That's actually going to be 6.0 because I have to round up because I only have 2 sig figs. 6.0 times 10 to the 22nd atoms neon. Okay, determine the mass in grams of each of the following quantities of substance. I have 557 copper atoms. That's key. And I want to go to grams. So I'm going to start by recognizing that, again, 6.022 times 10 to the 23rd atoms equals 1 mole, in this case, of copper. And then from the periodic table, I can pull the fact that 1 mole of copper equals 63.54 grams. So this time I'm starting with atoms, 557 Cu atoms. So I need to get rid of atoms first. And I can see right here that I had a relationship. 6.022 times 10 to the 23rd atoms, copper, goes on the bottom. And then I finished my equation here with 1 mole of Cu. That gets me out of atoms into moles. Once I have that, then we see, oh yeah, I have a relationship between moles and grams. So 1 mole of copper is 63.54 grams of copper. And then I put it into my calculator. Highly recommend using parentheses with the 6.022 times 10 to the 23rd, or else you'll end up with an enormous number when really you should have a very small number. And I'm going to multiply by 63.54, and I get 5.877 times 10 to the negative 20th, and I have 3 sig figs, so it should be 5.88 times 10 to the negative 20th. Again, really small number, which makes sense. We're trying to figure out the mass in grams of a very small number of atoms of copper. All right, now we're going to work with 1 copper atom. Again, should be a pretty small number. And it ends up being identical in the way that we treat this, because we're still starting with atoms. So we still have 6.022 times 10 to the 23rd atoms, copper on the bottom, to 1 mole of copper. And I need to go to grams, so I use the molar mass of copper, 63.54 grams copper, and that will give me 1 divided by 6.022 times 10 to the 23rd times 63.54 gives me 1.05 times 10 to the negative 22nd. Now, technically, this said 1 copper atom, so I'm going to call that 1 sig fig and say this is 1 times 10 to the negative 22nd grams. Number 34. Determine the number of moles of substance present in each of the following quantities. So I'm looking for moles, and I'm given in A grams of nitrogen. So I have to think, do I need Avogadro's number for this? Well, no, I don't. I don't have atoms or particles or molecules or formula units or ions or any of those things that Avogadro's number has. In fact, I only need a relationship between grams and moles, which I have from the periodic table. So I know that 1 mole of any substance on the periodic table is equal to its mass in grams. So 1 mole of N equals 14.01 grams of N. So I can take my 25.0 grams of N, and I can divide by 14.01 grams of N and multiply by 1 mole of N to change my units. 25 divided by 14.01 gives me 1.78 moles N. In letter C, it's a little bit different story. Here I have atoms of sulfur, so that should make me recognize, oh yeah, I have to use Avogadro's number here. But I don't have any grams of anything, so I shouldn't need to use the molar mass of the periodic table. In fact, I don't. So I have 8.50 times 10 to the 11th atoms sulfur, and I just want to use Avogadro's number to go to moles. So 8.50 times 10 to the 11th divided by 6.022 times 10 to the 23rd gives me 1.41 times 10 to the negative 12th. Atoms. Hold on. I meant moles. Sulfur, because my atoms have canceled. Number 36. Determine the number of atoms of nitrogen present in each of the following. So here we are. We want to find the number of atoms, and we want to find specifically the number of atoms of nitrogen. And in this problem, we're starting with grams of something that's not just nitrogen. So I notice here that in 1 mole of HN3, I have 3 moles of N. And I know that I need to do this because the problem asked me for just nitrogen, but I'm given the whole compound. So I know that at some point I'm going to have to use this relationship. Now we can start thinking, okay, if I start with grams of HNN3, and I need to go to moles of HNN3, which is really what that first step is, then I need the molar mass of HN3. So 20.0 grams HN3, the molar mass is going to be 14.01 times 3 plus 1.01. That's going to be 43.04 grams HN3 to 1 mole of HN3. All right, that's looking good, but I need to go to nitrogen. So now I'm ready to use my relationship that I have up here. For every 1 mole of HN3, I have 3 moles of N. That's great. Now I'm in nitrogen. What type of unit do I need while I'm in nitrogen? Well, I need atoms. So I got to go from moles of nitrogen to atoms of nitrogen. 1 mole of N. The only thing that we can use to get to atoms is Avogadro's number, 6.022 times 10 to the 23rd atoms, N. Notice here it's kind of important to write what your units are of. So like the fact that it's 1 mole of HNO3, excuse me, just HN3, because at this point we have moles to moles. And so we better know what we're doing there. So we make sure that you cancel the right units. So I'm just putting this into my calculator, and I get 8.39 times 10 to the 23rd. 8.39 times 10 to the 23rd. And that's going to be atoms of N. Box my answer. All right, letter D started with moles of N2O5, and we want to go to atoms of N. So I noticed that in 1 mole of N2O5, I have 2 moles of N. So I'm going to start with my 4.00 moles of N2O5, and I'm going to change to nitrogen because the question asked me about nitrogen. So it kind of makes sense to do that. 1 mole of N2O5, 2 moles of N, and then I need to go to atoms. So 1 mole of N is 6.022 times 10 to the 23rd atoms. N. Pop it into the calculator. 4 times 2 times 6.022 times 10 to the 23rd gives me 4.817, which is going to round to 4.82 times 10 to the 24th. And this is atoms. N. Looks like we have one more slide. Number 37. Determine the number of grams of sulfur present in each of the following quantities. So again, it says grams of sulfur. And when I look down here, I have S2O molecules. So since it's asking me for something that's a part of the molecule, I know that 1 mole of S2O will equal 2 moles of S. All right, so we know we're going to need to use that. First, though, I got to get all the molecules. 3.01 times 10 to the 23rd. Looks like I have an extra times 10. Or I put my 23 in the wrong spot. Should be over there. And this is S2O molecules. I need to get rid of molecules. And to do that, I need Avogadro's number. 6.022 times 10 to the 23rd molecules, S2O, is to 1 mole of S2O. So now I'm in moles of S2O. The question asked me about grams of sulfur, so I need to get out of S2O into sulfur, for which I'm going to use my conversion that I figured out over here. So 1 mole S2O, 2 moles of S. My last step is to go to grams of sulfur. So I look on the periodic table and see for every 1 mole of sulfur, there are 32.07 grams of sulfur. So 3.01 times 10 to the 23rd divided by 6.022 times 10 to the 23rd times 2 times 32.07. Ooh, look at that. It's 32.06, which really is 32.07. Why is that? Well, maybe you picked up on the fact that 3.01 times 10 to the 23rd is actually half a mole. And so we had half a mole, but then we multiplied by 2, so really it all came out in the end. In letter D, we have 4.50 moles this time of molecules. So we're ignoring the molecules. We're going to focus in on the fact we have moles. And it's of S8. So in 1 mole of S8, I have 8 moles of S. And from our earlier thing, we know that 1 mole of S is 32.07 grams of S. So 4.50 times 8 times 32.07. Whoa, that's a big number. I have 1154.52, but I can only have 3 sig figs, so it's going to be 1150. That last zero is a placeholder for me, grams of sulfur. And that concludes this session. Go ahead and look for the second integrity video in this group, where we look at problems from the rest of the sections in the chapter.